So if you want, you could solve this using Cholesky. In fact, because of the uniqueness of the QR factorization and the Cholesky factorization, A transpose A, if you were to do a Cholesky factorization, that is R1 transpose R1, this is the R1 from the thin QR factorization. So the transpose of R1 happens to be the Cholesky factor. So you get this factor without necessarily computing the QR factorization. But and Cholesky itself is still going to be pretty expensive. It's going to be order n cubed operations. Okay, so we go ahead and solve this. Also, to confirm that this is a minimum, the Hessian of this norm that we're trying to minimize is actually 2A transpose A. When the Hessian is symmetric positive definite, the critical point is a minimum. So that is verified here. Okay. Now, let's see, what else do I want to say about this approach? Did that. Okay. All right. So, first I want to mention why are they called the normal equations. If I were to rewrite this, I can say this is the same as saying A transpose AX minus B is equal to 0. Now, this seems like just a trivial algebraic manipulation to rewrite these equations, but this one is a little more telling because what this is saying is the residual of your least square system, B minus AX, which is going to be non-zero generally, is orthogonal to the range of A. In other words, it sits in your orthogonal complement. Because that's what this equation is saying. This is the dot product of the residual with all the columns of A. And that's why we know that the X that makes this happen, it's unique. Because what we're doing is, it's like quite a while ago, early in the semester, I was talking about projections. You're trying to find the best approximation of a vector belonging to a given subspace. And the way you do that is make sure that the error is in the orthogonal complement of the space you're trying to project into. Okay. Another thing I could point out about solving the normal equations is X is equal to, so that would be A transpose A inverse A transpose B. Now, if I go ahead and multiply both sides of that by A, so then I have AX is equal to A transpose A inverse A transpose B. Now because A is not a square matrix, I can't simplify any of this. I can't break this down to A inverse transpose because A inverse doesn't even exist in this case. So it turns out that AX is not equal to B, it's equal to this vector. But this matrix here, A transpose A inverse times A transpose, that is the projection onto the range of A. So remember I said at the beginning, AX equals B only has an exact solution, if and only if your right-hand side vector is in the range of A. Well, this vector is in the range of A. Now, so this is what the least squares problem does. It won't solve AX equals B exactly, but what it will solve is AX equal to the projection of B into the range. So that's how it's going to come as close as possible to finding a solution. Okay. Now, there's one other thing that I can reveal about the least square solution if I make use of something that I talked about a while ago, the singular value decomposition. So, I write A is U sigma V transpose. So this is the singular value decomposition, or SVD. So then, my solution to my least squares problem, so that's A transpose A inverse A transpose B. And now I'm going to fill in the SVD. Now, if A is this, A transpose is V sigma transpose U transpose. So then I fill in A, U sigma V transpose, inverse, and then I have A transpose again, V sigma transpose U transpose B. Now, I'll simplify this as much as possible. So this is the U's cancel because U is an orthogonal matrix. So now I have V sigma transpose sigma V transpose. Now, all of these matrices are square, so I can break this down into individual inverses. So I have V transpose inverse, sigma transpose sigma inverse, V inverse V, sigma transpose V transpose V. Now V is an orthogonal matrix, but here V inverse V, those cancel. And now I have, well, V is an orthogonal matrix, so its transpose is its inverse. So this is just going to be V. Now I have sigma transpose sigma inverse, sigma transpose U transpose B. All right. Now, this matrix in the middle of all these sigmas, well, sigma is a diagonal matrix, and the diagonal entries are the singular values. So here I have a diagonal matrix, it's n by n, with the singular values squared, but then I take the inverse, which takes 1 over the diagonal entries. And then here I just have the singular values on the diagonal again. So what ends up happening is, when I carry out this multiplication, so all this is n by n, and this is n by m. So I'm going to get an n by m matrix again. And what it's going to have is V, and then my diagonal matrix will look like this, because here I have a singular values to the -2 power. Here I have them to the first power. So I put it all together, I get singular values to the -1 power. So I have 1 over sigma 1, 1 over sigma 2, and so on down the diagonal. Everything else is going to turn out to be zeros. And then I have U transpose B. Now, suppose A was invertible. If it had an inverse, what would it be? It would be V sigma inverse U transpose in the invertible case. Well, I don't have that here because A doesn't have an inverse. But it's pretty dang close, because whatever non-zero singular values I have, I'm taking the reciprocals, and I have V at the start and then U transpose at the end. So it's almost like an inverse. So what we actually call this is A, the little dagger, called the pseudo-inverse of A. Now, not every matrix has an inverse, of course, but every matrix does have a pseudo-inverse. Take a singular value decomposition, you interchange the roles of u and v, and you take your reciprocals of whatever non-zero singular values you have. All other singular values that are 0, you just leave them 0. So it's as close as you can get to an inverse without actually having one. It has some other names. It's called like a generalized inverse. It's also called a Moore-Penrose inverse. So just as ax equals b in the square invertible case is x is a inverse b, x is generally a pseudo-inverse times b. So we can express the solution in the same way.